I think I'm talking. Yep, it's hearing me. That's a good thing, because that was a problem the other day. All right. Couple things before we start on the wonderful new math. I posted the practice assignments up in WebAssign. They're basically due the day of those days, but you don't have to do them. Like, they're not due, they're not graded. Those are literally just for you to have more practice. I figured I'd put them on the days that we taught it, so this way you know, like, okay, I want to go study this. I remember it was last Monday. That's the day it's there. So don't freak out. You don't have to do them. They're not due assignments that are graded. They're there just for you to practice more problems. So like today, the one for today was for section 2.5, which is what we're going to go over today. So that's all there. The only things you have to do in WebAssign is the homework ones. The ones homework for chapter 2, homework for chapter 3, and those are due the day of the test. So those are basically there to help you practice for the test. Anybody have any questions or problems getting into WebAssign and stuff? Is everybody good there? Okay. If you haven't gotten your book yet or your code, you can still sign in. You get 2 weeks free. Make sure you do that. It's on the syllabus. It's at tier. It's on my website too. So that'll get you into the class, and then before the end of the 2 weeks, you'll just have to put in the code you get from the book. So there's 23 of you in there now, and I know there's a few more, so still a few I'm missing in there. Remember, I haven't gotten the email yet, but I know it's coming. That's what I'm going to use to mark you as being in classes here. So please, please, please make sure you've gone in and signed into WebAssign. If you have not, and there's an issue, please come up and tell me after class. So I don't want to get you removed from class if you actually are here just because you're not signing into WebAssign. All right. Any questions on the other stuff we've covered so far? The section 2.1, 2.2, and 2.3. Okay. So we're doing good so far. All right. What's continuity mean? Okay.
No gaps.
That's the big piece, is that there's no gaps. All right. Continuity means that it continues going and there's no spaces, gaps, holes, asymptotes, things like that. Okay. So we're looking at continuity of a function. We're looking at it in terms of over its domain, does it have any blank spaces or holes or those type of things in it? And if it does, then we need to deal with those situations. Okay. All right. So continuity has a very specific definition. If the limit as x goes to a of f of x equals f of a, that means it is continuous at that number. Okay. So we're not going to be, we will look at a continuity over an interval, but a lot of times when we're talking about continuity, we're talking about it at a specific point. Does the graph exist at that point? So if the limit exists and it's the exact same thing as if I plugged in the number, that means it is continuous at that value. And remember, limit doesn't have, those don't have to be true. We've done quite a few situations where we found limits that to points where they didn't exist. Okay, so for it to be continuous at that number, that has to equal. That means there's a few things that's true. That means that f of a is defined at that point, and that a is in the domain of the function. So we can still have domain restrictions. That doesn't change continuity. All right. We also know that the limit exists at that point. And then we also know that the limit equals just the direct substitution of that value in there. Any questions with that? Basically, it's just reinforcing the idea that if it's continuous, we can plug the value in and get the answer out. We don't have to do anything special to find the value of that limit. All right. Let's look at these. Where is this function discontinuous?
3 and 5.
Yep, discontinuous. All right, so we've got, I've heard 1, 3, and 5 are the numbers that I've heard for a variety of people. Not everybody agrees with those numbers, but those are the numbers that I've heard. All right, so let's think about what we have just said about continuity. If it's continuous, the limit as x goes to a of f of x has to equal f of a. Okay, so that's what that states. So if I'm saying that a is 1, let's start off with that one. So the limit as x goes to 1 of f of x should equal f of 1, right? What is the value at f of 1? This does not exist, right? Does the limit as x goes to 1 exist? Yeah. I'm just going to make up some values here. There we go. So the limit would be 2. But the function does not exist. So is it discontinuous at when x equals 1? Yes. Okay. And that's discontinuous. Because the limit does not equal what f of a would equal. Okay. Does that make sense? All right. What about the 3? Does the limit equal f of a at 3? All right, so let's look at that one. Let's duplicate this slide. So I don't have to erase that. Goes to 3 of f of x equals f of 3. So what's the limit? What's the limit, or what's f of 3? We'll start with that one. -2. What's the limit as x goes to 3? That doesn't exist. It goes to 2 different values, right? So again, since those are not equal, that's also discontinuous. What about the limit of f of x as x goes to 5? What's the limit as f of x goes to 5? As x goes to 5? Yeah, we'll say 3. 2.5, 2. It does. I made those numbers up. So, what's the answer of f of 5? Like 5 or 6. Yeah. Are those equal to each other? No. So that's also discontinuous. So we've had 3 different situations. One where the limit existed but the function didn't. One where the function existed but the limit didn't. And one where the function existed and the limit existed, they just didn't equal the same thing. Those are all different cases of discontinuities. Okay? If I looked at the limit as it went to 4, let's say. So let's say the limit as x goes to 4 of f of x. Does that equal f of 4? So we're looking at like right there. So f of 4 is 3. What's the limit as it goes? It's also 3. So that point is continuous at x equals 3. So the function is continuous at that point because the limit equals the actual value that's plugged in there. Yes?
So like basically if they don't, and basically all of the situations could continuous.
Yeah, all those situations can be discontinuous. Yeah. Now, most times when you're looking at these, you're not going to be looking at a graph. You're going to be looking at the actual function, and we have to figure things out from that, which is what we're going to get into in a minute. But this is a great example of being able to show you what all the different cases could come up to be. So if they come out to be equal, they're continuous. If they don't, then they're discontinuous. All right. We have a few types of discontinuities. The first one, so this one up here, make it a little bigger, and then I will shrink it down a little bit afterwards. This one's known as a removable discontinuity. What do you think it means by removable discontinuity? So a removable discontinuity is one where I can simplify the function down and find the answer. Okay. So a good example of this would be, I'll make one up real quick. A good example of this would be this. So x minus 2, x plus 3 over x minus 2. So at x equals 2, the function is undefined. So there's a hole there. However, if I look at this problem, I could easily cancel out those x minus 2s, right? And my function would be the same as x plus 3. That's what's known as a removable discontinuity. That I can easily simplify the problem down and that discontinuity would go away and I could find that answer. Okay? So it is a discontinuity in the original function because it's not part of, and actually it's not part of the domain of that function because I have divided by 0. But I can remove it by simplifying the function down. Okay? So that would be a removable discontinuity. This one, when I have another point, it's still a removable discontinuity. I can still simplify this problem down to find that answer. This would automatically be what's known as a piecewise function. You're going to have multiple functions there. You're going to say when x equals 2, the answer is 1. So you can easily simplify down the original problem to find that limit. That's why it's also the same thing. It's a removable discontinuity. We also have these two situations. The first one here, the third one we talk about is an infinite discontinuity. These are ones that go to infinity. So they either go to positive infinity or to negative infinity. You're going to have an asymptote there. And this one right here, they use this example, but there's many examples that we can use for a jump discontinuity. These are known as jump discontinuities. Jump discontinuities are where the point where you're starting going in one direction and you're jumping to another. Okay, so that's a jump discontinuity. I'll show you this right here. That is also a jump discontinuity, where we're going to one point and then we're jumping over to another point. So it doesn't necessarily have to be that step. A jump discontinuity is that break point. What about this one? That point right there would be known as a what? That's a removable discontinuity. What about this one? That's also a removable discontinuity. Okay, so I have a jump discontinuity in this case and two removable discontinuities. I don't have an infinite discontinuity in this problem. All right, let's look at this one. Where is this function discontinuous? Okay, x equals 2. All right, and that's because that is, in essence, a domain restriction, right? Yeah. So, and this is one of those ones where when we're looking at, as this problem is stated right here, x equals 2 is a discontinuity. However, if I put this next to this equation, the function is continuous on the domain. Okay? Because whenever you're looking for discontinuities, you're looking for ones that are not part of the domain where it breaks. In this situation, because I gave you the domain restriction, I wouldn't necessarily have a discontinuity there. Okay? So when we're talking about functions, they are continuous over their domain unless we have a restrictions built in there. So x equals 2 is a discontinuity because they don't give me that domain restriction. So we're looking at the entire restriction there. Now, is it a removable discontinuity or no? How do you know? Okay. If you factor the top out, you get, was it x plus 1, right? Over x minus 2, which means we can cancel out those two. So it is a removable discontinuity. Okay. Do they always have to be a removable discontinuity? So if I take this problem right here, so right now it's 2. So that's what it ends up looking like if you graphed it. However, if I just change that to 3, I still have a discontinuity at 2, right? But it's no longer removable. Okay. And notice how the equation actually, like the graph changes too. So it's pretty easy to be able to see that's removable, that's not. Yeah. That would be an infinite discontinuity. Yes.
So are discontinuities just domain restrictions?
They can be. A lot of times. Sometimes it depends. Like in most of your situations that you're going to see, they're going to end up being the domain restrictions. The situations where they're not is where you have piecewise functions and things like that, where the functions kind of jump or they have different equations for different places. That's where you're going to have those more complicated situations. So, And most of the easy functions, yeah, is just going to be where the domain restrictions are. All right. Now this one. Is it discontinuous at 2? Oh, sorry. Is it discontinuous at 2? Okay. All right. So if I was to graph this one, what was it? 2, 1? That's how that would look. Okay. So there's a hole there, and it's there. That would be another removable discontinuity. Right. What's the discontinuity in this function? This function is not discontinuous. This function is continuous everywhere. Okay. So the reason I wanted to show you that one is don't automatically make the assumption that it's discontinuous because it's a piecewise function. Okay. Sometimes they use those piecewise functions to fill in the holes. All right. In this case, that's exactly where that point should be. So this function is now completely continuous. All right. There is no discontinuity because that extra piece filled in the hole. My limit, if we're looking at it the way we were looking at it before, my limit as x goes to 2 of f of x is 3. Because if I simplified that down and plugged in 2, I'd get 3. F of 2 is also 3. Since they're equal to each other, therefore, they're continuous. Okay? It's always those little things like that that are going to get you. Okay? And they can come up. A lot of times, honestly, this situation is one of those ones that comes up quite often because you'll have a function that has some breaks in it, but you don't want those breaks. So it works everywhere else except for these certain spots. So you're going to use a piecewise function to fill in those holes. So that can happen quite often. So just keep that in mind. All right. I wanted to show you this one because this is something that normally that doesn't show up quite often. However, depending on what your major is and things like that, especially if you're in computer sciences and those type of things, you will see this symbol. This symbol does come up quite often in computer science. This is what does it look like? All right. So absolute value kind of gets rid of your sign, right? Makes everything positive. This one gets rid of your decimals. This one makes everything the integer. Okay, so basically it's like it truncates. Okay, so f of 1 in this case, I'm totally going to chop out of this, but that's okay, equals 1. If I had f of 1.25, That also is 1. No, that's actually what I was just about to show you. That's also 1. It truncates. Okay. So what this graph looks like, if I can actually, let's see if it'll actually let me graph it. Yeah, this is that step graph. I don't know if I can graph it on Desmos. We're going to see. There we go. Well, kind of, but this works. So that's what the step graph looks like. So at 1, it is all the values there. That's always going to be 1. And when you get to 2, it jumps to 2. So it has basically an open circle here and then a closed circle at that next point. Okay. That's known as your step graph. So in this case, do I have discontinuities? Yes. All right. I have a discontinuity at every integer. So every time the equation equals 1, 2, 3, 4, 5, doesn't matter. I have a discontinuity. They are not removable and they are not domain restrictions. Okay. So this is one of those situations where it isn't a domain restriction. This function is just by definition discontinuous or discontinuous. Okay. So why this comes up in computer science a lot of times is because a lot of times when you want to do calculations, you only want the integer values. And this allows you to do that truncation. There is one that rounds. If I did the rounding, this one's that, I think I got that one here too, yes. You'll notice it looks very similar. Because why? Where is the jump discontinuity in this problem? Yes, it's at the 0.5s. So once it gets up to 0.5, it's going to jump up to the 2. So it's every half integer plus 0.5 basically is going to give you that jump discontinuity. Because once it hit 1.5, it's going to round up to 2. Okay? But the graphs they're both step graphs. Okay? All right. Questions with those? All right. Yes.
We know if it's gonna be like around or.
Oh, it would have to tell you.
Oh, okay.
Yeah, those would have to tell you. Like that symbol right there means integer. That means it's a truncation. I can't remember. There is a symbol for rounding in there, but I can't remember it off the top of my head. So I want to pull up a problem really quickly. Actually, let's do this one. Because this one is nice. All right, let's look at this. So far, we've looked at equations for most of it, or we looked at a graph. However, we can also look at real world situations. First one's true everywhere except for New England, where you never know what temperature it is. All right. So the temperature at a specific location is a function of time. Is that continuous or discontinuous? Continuous. Like it can't jump between temperatures, right? So if it's 37 and it goes up to 45, it's hit every single value between those 2 points at some point. Okay. Good. The temperature at a specific time is a function of distance due west from New York. Would that be continuous or discontinuous? Could the temperature jump instantly between two places?
Yeah.
Right, but even so, like, okay, so let's think about we'll think about a simpler situation. Okay, let's take your house. You're walking due west from your house. Could the temperature go from 35 to 45 instantly as you're walking? No. Eventually, while you're walking, the temperature is going to change gradually at some point. Like it's still going through all those temperatures, and you're still going through all those distances. So that's still continuous. Okay. So yes, the temperatures will be different, but to get to that other temperature, you've had to go through all the other temperatures to get there. The altitude above sea level is a function of the distance due west from New York. There you go. All right. There is a possibility of a vertical wall. That, like, okay, that's possible. Right? So, or even a building, like buildings are basically vertical. Like, so your distance above sea level, if you're walking, you'd have to jump that distance. So your altitude above sea level as a function of distance to west from New York is not. There can be a discontinuity there. The cost of a taxi ride is a function of the distance traveled. This is an old question. When was the last time anybody here took a taxi? Not an Uber or a Lyft, a taxi. Okay. Yeah, like this is one of those questions that has not aged well. Yeah. So, and actually, as crazy as this is going to sound, I've never taken an Uber or Lyft. I grew up when we were told never to get into a stranger's car, especially one that we never met on the internet. But so I'm going to assume they work very similarly, and it's based on mileage, not necessarily like if you go a half a mile, is it literally like half of what the mileage is going to be, or is it like a set price that you pay? Okay. All right. So it's in these situations, it's probably going to be more like a step graph. Like you're paying a specific thing for mileage. Even if you go a quarter mile, you're paying that whole mile type thing. Okay. So in this situation, it would be discontinuous. It would be like a step graph, right? And that's actually how a taxi works. It's you pay a flat rate to get into it, and then you pay an amount per mile, but it's rounded to the nearest mile. It's not broken down by miles.
Oh, I just rounded to the half mile. I was gonna say this.
Some are rounded to half mile.
It's just a flat fee, and then like the distance is.
Yeah, but
It's just that's just a wide.
you got to remember when taxis and stuff were like came around and stuff, we didn't have GPS and everything else.
Yeah, I guess you can't actually charge the close.
Right. So it literally used the odometer, and it every time the odometer clicked over to the next number, that was a mile. That's how it actually charged you. It literally went off the odometer. The current in a circuit of lights in a room as a function of time. Anybody in here in electrical engineering and those type of things?
I think this could.
Is it continuous or discontinuous?
I think it should go over time.
Why?
Because you can, I don't know if this is gonna make sense, but like, if it is like, you got a whole circuit, you can move it. So is that movable? Is that, or am I not like thinking? You actually have an.
Yes, I totally understand what you're trying to say. Doesn't quite work that way.
Circuits are always either on or off, so they can't, there's never like a gradual change.
All right, electrical engineers. How's the first of all, how's the current go to your light bulb? So we have what types of current? We have AC and DC. We have alternating current. We have direct current. All right. Your phones typically use direct current. It stays a specific current. Okay. Your lights, if I turn the lights on in this room, they are alternating current. Okay. The lights in this room flicker. So if you turn them on, they flicker. You don't see it because they flicker at 60 hertz, which is the exact level that the human eye cannot detect. Okay. The actual electricity coming out of the wall is a sine wave that goes up and down 60 times per second. So the actual current that's coming out to these lights goes up, goes down, goes up. And every time it goes up and goes down, it's continuous. It hits zero. That's when the light shuts off. And then it comes back up. That's the flicker. So, but it does it so fast, you can't tell it. All right. However, if I turn it off, does it go instantly to zero? It does. The current stops.
Oh, yeah, but if you're using like a filament, that is to pull down
Well, that's totally different.
for like.
Yes, that's not, there's no current coming to it. It's literally just, it's got to cool down. For the bad part about it is the first thing I thought of was my 3D printing was filament. I'm like, no, he's talking about the actual filament in a light bulb, which we don't use very often anymore. So your light bulbs typically are either gas, like your fluorescent bulbs and stuff like that are actually a heated gas now, or the LEDs, which is a diode that actually turns on and off. Most incandescent bulbs don't exist anymore. We don't really use those. Those are the ones that have the filament in it that heat it up. All right, because they were very inefficient because they literally are turning electricity into heat, which is then turning into light. And that's a very inefficient transfer of electricity. Very wasteful. That's why we went to more of the gas with the fluorescent bulbs and then now the LED bulbs. So while the light is on, it is continuous. So absolutely. If the light is on, it is absolutely continuous. But if you shut it off, the current stops immediately. It's breaking that battery point. So it doesn't gradually go back down to zero. It's instantly back down to zero. So when the lights go off, that would be your discontinuity. But when they're on, it absolutely would be a constant or a continuous current. So yes, it's continuous while on, but if you turn it off, that's the discontinuity.
Just think of it as the word time, because time is forever. It keeps on going.
Well, yeah, but I could have breaks, like I could have those stop points, and that's going to be your discontinuity, where it's just going to go from whatever it is to zero. All right. So now, if you think about your battery life in your phone over time, is that continuous or discontinuous? What?
Continuous. If it's not broken.
Yeah. That's going to be continuous, right? So, right. But even that, if you turn it off, the battery is no longer discharging. So the battery is going to stay at a constant charge at that point. Right. So it's still the battery life is still continuous. It's staying there. All right. Or if for some reason it doesn't work good and it's draining a little bit, it's still going to be continuous. It's going to hit every single percentage and all the numbers between the percentages down to zero. Okay. So that would be continuous. So you can start to look at how, like, real life situations, how continuity works. All right. We have two special cases. We do have situations where my function stops. All right. So we've talked about dividing by zero. Dividing by zero is when that's a domain restriction. And those will either be removable discontinuity, removable discontinuities, or they will go to infinity. What is a domain restriction that stops at a specific point and doesn't go past? Square roots. What's the domain restriction typically in the square root? Right. So my square roots have got to be, whatever the number is underneath has got to be greater than or equal to 0. So that would be an endpoint. Okay. We can figure out continuity at that point by looking at one direction. Okay. Remember, we can have the limit as x goes to a, the positive, when we're looking at it coming from the right, or the negative when we're looking at it coming from the left. So at situations where the point does not, the graph or the function does not continue past that point, I can look at a one-sided limit to determine continuity. And I would say it's continuous from the right or continuous from the left at those points. When we're looking at it as continuous on an interval, that's where we, at the endpoints, we would look at it coming from the left and coming from the right, because we don't go past those endpoints. Okay. So most situations when we're looking at continuity, we're going to look at the regular limit where we have to look at both directions, but at endpoints, we would look at the one-sided limits because the other side doesn't exist. All right, so let's look at this problem. We want to show that this function is continuous on the interval -1 to 1. And it's including -1 and 1. That's what those brackets mean. So how would I, let's just look at the interval. So how would I show that that's continuous? I need to show that the limit as x goes to a of f of x equals f of a, correct? So first thing I'm going to do is I'm going to say a is between -1 and 1. Okay. So I'm going to do the limit as x goes to a of 1 minus the square root of 1 minus x squared. All right, so now, can I just plug the a into x as it stands right now? There's no, well, can I? Probably, but I need to state why I can do that. All right, so let's use some of those laws that we looked at on Thursday or Wednesday. If I ever say Thursday, it's because I count 2 classes, Tuesday, Thursday. Let's use some of those laws that we looked at last Wednesday and see how we can simplify this down. So I'm only looking at the limit of something that I know I can do. All right. So remember, if we have subtraction, I could easily split that up and look at the limit of each one, correct? So I could say the limit as x goes to a of 1 minus the limit as x goes to a of the square root of 1 minus x squared. Remember, I can do that? What's the limit as x goes to a of 1? That's just 1, right? Okay. So I now have 1 minus the limit as x goes to a of the square root of 1 minus x squared. All right. Can I put the limit inside of a root? Was that one of the rules we looked at? The laws we looked at? So one of the laws we looked at said I could do this. The key piece though is that part still has to be continuous. Okay. So I can do that as long as I know that function exists over that domain. All right. And now I can do the same thing I did here. I can split that up, right? So I can look at the limit as of 1 minus the limit of x goes to a of x squared. And that one is simple, right? That one I can actually, now I know I can plug in the a to that. So this does equal 1 minus the square root of 1 minus a squared. And that would be the exact same thing as if I just plugged a into the problem, correct? So this limit is continuous on that interval. However, now I have to see, is it continuous at when x is negative or a is -1 and when a is 1? So I have to check the endpoints. Yes. Sure.
I don't know where.
That was gonna be the next question. Do you know where?
All that we proved here was that A could go.
Yes. Yeah. So okay.
Why couldn't we just do that from the get-go?
You okay.
Same thing.
You could. So there's a difference between when the question asks you what the limit is and when the question asks you to show that it exists. Okay. So because we have the rule, so in essence, this is almost like a proof. We have to prove why that's true. Okay. So if I know that's continuous to start with, I don't have to do, the problem doesn't exist because that's what the question was asking me. So I have to prove that it's continuous by using those rules that allow me to do that. Okay. So the first rule was I can split this up as long as these two things are continuous. So I know one's continuous, so I can do that. I know the square root of this is if I plugged in any, as long as the number is not 1. Okay, this doesn't become negative, but I don't have to worry about it. I know that that's, so I'm able to split that up. I know that it's, the roots typically are continuous as long as x is greater than 0, so I can bring it inside. And then I can do the same splitting then. So it's basically just proving that it works. Okay?
And what we
So
proven
when they
is-
say show it, you have
It's basically proving it out, yes.
and what we've proven is that
That the limit equals the exact same thing as if I just plugged in the f.
that the two, that -1 and +1
Also work. Correct. So right now we know that -1 to 1 works, not including the endpoints. Notice that my a does not have equal signs underneath the root, the inequalities. Because I haven't tested the endpoints yet. Now I have to test the endpoints. All right. So we need to show that the limit as x goes to -1 from the right side, because we're going that direction, of f of x equals f of -1. So what is if I plugged in -1 to the problem, what would I get? So -1 squared is 1. 1 minus 1 is square root of 0 is 0. 1 minus 0 is 1. So this side comes out to be 1. To show the limit equals that, we need to look at either a graph of it or we can do the table of values. But we need to see that that equation also goes to 0. So I'm just going to look at a graph of it just because it's simpler. And as I'm going up this graph here, it's getting closer and closer to 1. So the limit of this also equals 1. So I know at -1 it works. Now I have to check the positive one, the same concept. This time we're looking at it coming from the left side. Okay. Of f of x equals f of 1. If I plugged 1 into that problem, what do I get? I get 1. And if I look at the graph, I'm going from the left side to that point. It's getting closer and closer to 1. So the limit also is 1. So that means it works at +1. So that means I've now proven my interval work is continuous from -1 to 1.
You do all the steps you did before, or could you just do that and that's your proof? That's how it works.
So no, so I still have, this shows me the endpoints. So you could do this the same way, but you'd have to plug in every single number between -1 and 1. And I don't think you're going to want to do that because you're going to be here forever. So that's part of the problem. Like people go, oh, if I just plug in a few numbers and it works, then it must work. Well, on some situations, yes, but there could be a number in there that doesn't. And it might not be a number that you normally would check. So that's why when we're proving things, a lot of times we use variables to prove it because the variable doesn't matter which letter is going to be or which number goes into it. Okay, that's why we use the rules to be able to break that down and say, okay, this is the same as this based on that law that I have. This is the same as this, so now I can plug that in. Okay, so you'd just be there for a while. All right, so these functions are continuous for every single number in their domain. Okay. The key is in their domain. Because not every rational function is completely continuous. They have asymptotes and holes. So, but those won't be in their domain. Therefore, they'll be continuous on their domain. So polynomials are always, their domain is all real numbers and they are always continuous. Rational functions are continuous at everyone in the domains. They have those domain restrictions when you can't divide by 0. And those will either be a removable discontinuity or a infinite discontinuity at those domain restrictions. Your root functions, your even roots, has domain restrictions. They have to be greater than or equal to 0. Your odd roots do not. They're all real numbers. Your trigonometric functions, sine, cosine, tangent, sine and cosine, all real numbers. They're always continuous. However, your tangent, secant, cosecant, cotangent have domain restrictions. They go to infinity at certain points. So, but they're continuous between those domain restrictions. Your inverse trig functions are always continuous. They're continuous for all real numbers. Exponential functions, continuous for all real numbers. Logarithmic functions, continuous when they're greater than 0. So their domain restriction is it has to be greater than or equal to 0. Or sorry, greater than 0, because 0 doesn't work either. Okay. And the same thing goes with real life examples. They would be continuous on whatever the domain is. Okay. So if you go to mail a package, the thing the post office wants to know is the volume of that package. That's how they determine some of their fees. What is the domain restrictions for volume of a package? What can the volume not be? 0 or anything negative. Right, can't have negative space. So your volume has to be greater than or equal to 0 or greater than 0. So that's the domain restriction. As long as I have that, the answer is continuous. Every value after that point would work. Okay. All right. Find this limit. What's the domain restriction? Almost. 5/3. So in this case, x does not equal 5/3. That's the domain restriction, right? Is -2 in the domain? Then it's continuous there. You can just plug the number in. Okay? As long as that limit doesn't go to the domain restriction, you can just plug the number in. All right? Because we now know that it is continuous everywhere else. And if it's continuous, the limit equals the value you get when you plug it in. So this limit is just -2 to the third plus 2, -2 to the second. So -8, -8, -1 over 11. Okay. So as long as your equation is one of these functions and the value you're looking for is in the domain, just plug it in. You're done. You don't have to do anything. Because we know it's continuous at those points now, we can just plug those values in. The key, though, is you need to know what the domain restrictions are. So for any value except for 5/3, I can just plug the value into this problem. Where is this function continuous? So this is asking the opposite. Another way to ask this question is what is the domain of this function? Okay. Those would be the exact same question. All right. What is the domain, or where is it continuous? Because where it's not continuous is going to be the pieces that are not part of the domain. All right. So anybody have an idea of how to start this one? Okay. So let's look at the pieces and find where they are, where their domains are, or where they don't work. Okay. So let's look at ln of x. Where does ln of x, what's the domain of ln of x? All, not including the 0. Yes. So my domain is 0 to infinity. Okay, because ln cannot, you can't find the ln of 0. I can find the ln of any number up to 0, but not 0. All right. What about the arctangent? Remember, tan -1 and arctangent are the exact same thing. Anybody remember? Does anybody remember what that means or what that symbol is? It is the inverse. It's not the reciprocal. It's the inverse. So what's the x? What is the answer? What are my answers going to be? So in a typical tangent function, you're given the angle and you're finding the ratio for that angle. All right. So you're going to find the sine of 90 degrees and you're going to get 1. Okay. So the inverse would be me telling you sine of 1 and you telling me 90 degrees. Okay. So is the angles continuous? Yes. So there is no domain restriction for this. Because I'm going to get any value I want out of this. I plug a number in, I'm going to get an answer out. So in this case, this is infinite. Okay. The other way you can do this, and you will see this quite sometimes, is you'll see that symbol. I'll rewrite this a little bit better. That stands for all real numbers. The other one you'll see sometimes is this. It's not a 2. It's actually like a double barred I. Make it a little bit better. This is all integers. Okay, those are a couple that you'll actually see. The other one you see, but not very often, is that, and that's all complex numbers. Won't see that very often, but those are the 3 weird symbols that will pop up sometimes. Just to keep in mind. This one is the one that shows up a lot because it's easier to write that than negative infinity to infinity. All right. All right, let's look at the denominator. X squared minus 1. What's the domain restriction for that? Okay. As that sits right there, is there a restriction on it? No. So as it sits right there, there is no domain restriction. Okay. Now, There is going to be a domain restriction because of the way that it's written, because it is a rational function. But in essence, that right there is continuous for everywhere. Now, since it is in the denominator, I do have some restrictions. So I would set that equal to 0 and find it. So x squared equals 1. So x equals plus or minus 1. Okay, cannot equal that. So since this is in the denominator, I know it would work from negative infinity to negative 1, negative 1 to 1, and then 1 to infinity. Put the union symbol between those because I forgot to write the union symbol there. Okay, since it's in the denominator, that would be my restrictions. All right, now I got to put all this together to find my domain for my original problem. So my bottom is this. My top, the only restriction I have is that. So somehow we've got to combine these. Is this part needed? No, because that doesn't exist in my top, right? So that's not there. What about this part here? Part of it does. Okay, so my domain of my final answer. So 0 to 1, because before 0 doesn't work. And then from 1 to infinity, because I still cannot include that 1. So that is where the function is continuous. Okay? Does that make sense? No? All right. So let's see. What numbers can go at the top? All the positive numbers, right? What numbers can go on the bottom? Everything except for 1, correct? So I kind of got to put those together. So the negatives on the bottom don't matter because the negatives won't work on top. So I can eliminate those. So I can eliminate everything below 0. So that's why it's now from 0 to 1. Okay? I still have to have that breakpoint for 1 because 1 doesn't work on the bottom. So that's why I have the 0 to 1 and the 1 to infinity. And that it's all parentheses because that 1 doesn't exist, that 0 doesn't exist, and infinity can never exist. Okay?
So it sounds like that it's easier just to break up into.
Break the pieces up, look at each one, and then figure out how they're going to combine together again. Because that's the thing about the functions is that when you're looking at the continuity or domain or any limits and stuff like that, you can break them into pieces to look at each one individually, and then put that final piece back together. All right. Continuity really comes into play in what's known as the intermediate value theorem. This won't be that much. This is like the culmination of everything we just did. So the intermediate value theorem states that as long as f is continuous on the interval, every single number, there exists a c or some number in between those points. As long as it's continuous between f of a and f of b, there exists a number where f of c equals that number. Okay, so if I'm picking a number between a and b, and I know it's continuous from a and b, there is a value that works. Okay, which if you think about what we just talked about with continuity, that kind of makes sense. That's kind of the point, right? If I know it's continuous over there, I should be able to find a value for it between those two. The thing why this is so important and actually why you use this quite often is for situations like this. So I want to know that there's a solution for this equation, somewhere between 1 and 2. What's the solution for the equation? That's where typically you set the problems equal to 0, right? Where it crosses the x-axis, so it's your 0, your roots, things like that. So if you remember from pre-calculus, finding roots is very important, all right? Because that helps you factor things out, break things down. So now, if you could factor things and stuff like that, that makes your life real easy. Right? You can find the exact value. But sometimes I can't find that exact value. But I know it's somewhere between some values. Okay? So if we were to look at the graph of this, so if we were to look at the graph of this, there's a solution somewhere between 1 and 2, but I can't find its exact value. We want to use what we know about the intermediate value theorem and continuity to prove that that number exists. Okay? So we're going to plug in 1 and 2. So f of 1 equals what? 4 minus 6 is negative 2 plus 3 is 1 minus 2 is negative 1. Oh, thank you. And then we plug in f of 2. Yeah, 12. So my interval is from 1 to 2. F of A is negative 1. Or f of 1. And f of B is 12. So on this interval from 1 to 2, every single number between negative 1 and 12 has to exist. Okay? That's what the intermediate value theorem states. On the interval from 1 to 2, every number between negative 1 and 12 has to exist. Which includes what most important number? 0. So since it goes from negative 1 to 12, zeros between those numbers, 0 has to exist. So there is some value between 1 and 2 that if I plugged into this problem, I'm going to get 0 as my answer. I don't know what it is. I just know it exists. Okay?
Can you back to the log really quickly? The one
Yeah.
that's like before?
That one?
No, but after that.
Oh, the log.
Yeah.
The log.
That one.
Gotcha. Sorry, I heard log. Log. No. No, the intermediate value theorem just states there exists a number. So the goal is to say, okay, I know somewhere between 1 and 2 that it's going to go there. All right. So now we can become more specific. We can narrow that number down. All right. But even at that point, we might not be able to find the exact value of it. So let's think about a real life situation to where this is. So like if you're looking at, so great example, SpaceX. They launch rockets up. They're the first company ever to launch a rocket up into space and then capture the rocket and have it land on a boat in the middle of the ocean. Okay? Do they need to know exactly where that rocket's going to land? Okay? Down to what precision?
So whatever the area.
Right. They don't need, so there's a very distinct, so in mathematics, exact means an infinite number of decimal points. They don't need that. They need a very precise location, but they don't need an exact location. Okay? So, using these laws, they can find that precise location down to maybe 1,000th or 100,000th of a degree of latitude and longitude. And that's enough precision for them to do it. And that's where this is. They know it's going to be somewhere in between this, but if they're a foot off on either direction, that's fine. Okay, because it's still going to land on the moon. It just might not be on the X in the center of the moon. All right. So that's where these rules come in. You might not find the exact value, but you can get close. Your calculators do this all the time. Your calculators estimate and round all the time. You don't see every single possible number on your calculator. A computer is not going to give you every single possible value of the number going out. It's going to give you to a specific decimal point. Right? And depending on how precise the computer is or the calculator is, the more decimal points you can get out of it. But it's never going to be exact. And even in Desmos, when you look at it, that point right there, it's only precise to 3 decimal points. So if I took this and plugged in, let's see what we get out when we plug in scientific. So 4 was 1.22220. X to the third, X 6, X plus 3, X plus 1. 2, 1. That's the third. Is that 0? No. Close, but not 0. Okay. So even at that point, 1.221 is not the answer. It's close to the answer. And if we plugged in 1.222, now it's above 0. So I know the answer is somewhere between 1.221 and 1.222. So we can do 1.2215. Now I know the answer is between 1.221 and 1.2215. So I can now keep narrowing it down to find that point, but the intermediate value theorem allows me to do this. Okay, that's where that power comes into play. And that's actually how a lot of the stuff, the technology and stuff we have today works. Because if we didn't have these rules and stuff, we didn't know that worked, then we wouldn't be able to have the computers and technology to be able to do those estimations. Okay. So that is the intermediate value theorem. And that is it for today. If you are not in WebAssign, you need to be in WebAssign today. Okay? Because I know that email is coming. It very well could be in my email box right now. And I'm going to only have a few days to do it. So make sure you get into WebAssign today if you are not already there. All right? Next week is your test. It's next Wednesday. We will have a review on Monday. Next Wednesday is your test, yes, for chapter 2. If you have any questions, feel free to stay around.